All right, so taking a look at a Newman projection. Let's do a couple things first. Let's practice rotating 60 degrees. So you got to remember, this is a circle. How many degrees are in a circle?
360.
360, very good. So between fluorine and this OH, how many degrees is that? 60. Because from fluorine to the CH3 is 180. Very good. So from fluorine to OH would be, this OH would be?
90? No.
120. From this fluorine to this OH would be 120. So we're going to rotate 60 degrees. We're going to rotate between carbon 1 and carbon 2. Here, let's rotate it clockwise. So that'll be to the right. Clockwise to the right. Let's keep this, the back one still. So let's rotate C1. So rotating carbon 1. So the back will stay the same. That does not change. And when we do this, we started with a staggered conformation. We're going to move to a eclipse when we do a 60-degree rotation. So now the H and the fluorine are on top of each other. The other OH is there. CH3 is here. This is still carbon 1, carbon 2. So now let's convert this into a wedge and hatch structure. So let's draw a straight line. Carbon 1, carbon 2. So if I'm looking at it down here, at my head would be both the F and the H. So they're both in the plane. See that? So H is on carbon 1, so that's there. F is on carbon 2, so that means, right, if they're in the plane, that means they don't have wedges or hatches, and we'll do the same thing with this next. So if I was looking at this, what's on my right hand? OH. And I like to think of it as turning to the right when I do this. So the wedge part would be, both of them would be OHs. And the hatch part would be, what's on carbon 1? The H or the CH3? CH3. And then the H would be there. This is showing, with wedges and hatches, this exact same structure, an eclipse conformation. All right, let's take a look at this one now. See if we can turn this one into a wedge and hatch. So same starting point, 1 and 2. But now when we look at this, we have something at our head, but also something at our feet. So what's at our head? It's the F, and that's on carbon 2. So that would be there. What's at our feet?
CH3.
So that'd be down. Now what's up and to my right? So that'd be the wedge. And what's on the same side of that OH? The other OH. But notice how it has to be, right? The wedge has to be down this time, not up. Thing that's hatched to my left would be the H, and the other thing would be hatched to my left but down would also be the H. All right, so got to look at it, and I always like to turn to the right, perspective-wise. So this would be my right hand up to the right, way to the left, but up, CH3 down. That's the way you can translate from a Newman projection to a wedge and hatch. You should be able to do this as well. Take a wedge and hatch and translate it back to a Newman projection too. All right, so here's a chair conformation. So there's a chair. So just a refresher for chairs. Chairs are rings, right? And the rings have tops and bottoms, right? So let's do a quick exercise. Let's circle everything that's on the top part of the ring. So is the fluorine on the top part of the ring? No, it's pointed down. Is the iodine pointed up or down? Up, so it's on the top part of the ring. The chlorine, is it pointed up or down? Up. NH2, up. Bromine, OH, down. Now notice up and down has nothing to do with axial equatorial, right? If you're up, you're always up. If you're down, you're always down. Now you can be axial down, and then after the ring flip, you'd be equatorial down, right? You always are down. If you're down, you're down. If you're up, you're up. So let's do quick, maybe take this and try to do a ring flip. So what happens with the ring flip, this carbon, the head of the chair and the foot of the chair, right? You can see the chair. The head becomes the foot, and the foot becomes the head, right? It pushes down, so it's actually this way. You go boom, boom. All right? So to draw that, we draw it the other way. Let's number these carbons. 1, 2, 3, 4, 5, 6. So carbon 1, which was the foot, now becomes the head. So that'd be right here. That would be carbon 1, 2, 3. 4, which was the head, now becomes the foot. So that's number 4, 5, 6. All right, so that's the first thing you gotta be able to do. Now we're going to go to every single carbon and say, well, what's on that carbon, and was it up or down? If it's up, it's staying up. But if it was up and axial, now it's going to be up and equatorial. So let's look at carbon 1. That nitrogen is up or down? Up. And is it axial or equatorial?
Equatorial.
So now it's going to be up and
Axial.
axial. So that'd be up here, the top of the flagpole. Carbon 2 has a chlorine. Right? That chlorine is up or down?
Up.
Is it axial or equatorial?
Axial.
Axial. So now it's going to be equatorial, but it has to be pointed up. So it'll be up this way. Carbon 3 has an iodine. Is that up or down?
Up.
Up. Is it axial or equatorial?
Equatorial.
So now it needs to be axial and up. 4. So fluorine. Is it up or down?
Down.
Down. And is it down axial or equatorial?
Equatorial.
It's equatorial. So now it's going to be axial and down. Carbon 5 has an OH on it. And it's down. And it's down and axial. So now it's going to be down and equatorial. Number 6 has a bromine on it. That bromine is up or down? Up, and it's axial, so now it's going to be up and equatorial. Very good. Nice, so that's the ring flip. We should be able to do that. So, all right, so now let's take one of these chair structures and put it flat with wedges and hatches in a cyclohexane ring. So it doesn't matter which one I choose, because the cyclohexane ring is the wedges and hatches. That is, if you're up, you're always going to be up. So if you're wedged, you're always going to be wedged. So I consider the up to be the wedge, just as when I, in my own head, I like to do it that way. So 1, 2, 3, 4, 5, 6, and this is arbitrary. The numbers up here were arbitrary too. There's nothing about naming here, it's just arbitrary. So on carbon 1, I have an NH2. Should it be wedged or hatched? Wedge, because I consider wedged up. I mean, it really doesn't matter which one you choose, right? As long as, what should all be on the same side? The NH2, the chlorine, the iodide, and the bromine all need to be, if they're all wedged, that's okay. They all have to be hatched, right? What's on carbon 2? That's chlorine, so it's on the same side or the different side as NH2? Same, so it needs to be wedged as well. Carbon 3 has iodine. Is that up or down? Same as this guys? Yes. Very good. Carbon 4 has a fluorine. Is that fluorine on the same or opposite side of these?
Opposite.
So it's going to be hatched. Carbon 5, the OH, same or opposite?
Opposite. Or same as fluorine.
Same as fluorine, that's right. Yep, opposite of the other ones. And then 6 is going to be the same side as OH or the NH2. NH2. So the bromine is going to be wedged. Right? So this picture right here represents both of these chair structures. Right? Because this picture doesn't this tell you axial or equatorial? No, but it tells you up or down.
Yeah.
Right? What's on the same side as each other, but it doesn't tell you what's axial or equatorial. So both of these represent this. Okay, so taking a look at a cyclohexane ring, and we're going to draw some chair structures of this, and we'll figure out which chair structure is the most stable or least stable. So the first thing we need to do is just number these, and I'm just going to number it in an arbitrary fashion. There's nothing to do with nomenclature here. So I numbered those, and now I'm going to start drawing a chair. And just for ease, I'm going to put 1, 2, 3, 4, 5, 6. So if I look at these substituents, I should get an idea about what I want to be equatorial axial. So what do you want to be, what are some things you want to be equatorial? What are the things, what kind of substituents on a ring do you want to be equatorial? The bigger things. So which of all these things, which is the biggest? On which carbon? Which carbon has the biggest thing on it? Iodine's big, but this is a lot bigger. Right, this is 4 carbons, 9 hydrogens. This is packing a pretty big punch. Right, so this is really big. Right, so this tert butyl group. So we want to make that, if it's really big, we want to make that axial equatorial. Equatorial. So let's just start off doing that. So if we do that, actually I'm going to redraw my chair then to make it more consistent for how I like to draw them. Or we can draw it. We'll draw it the way it's written here. So I like to make this axial or equatorial, right? But right now I only have at carbon 3, what positions do I have? I have axial up and equatorial down. And the way I like to think about this, do I like to think of this wedge as up or down? Up. So let's flip this. Let's just save ourselves a quick second here. And we'll flip it. Now you could have done, right, and gone through the process of doing this all over, and realized, oh shoot, that thing's axial, that's not good. 2. 1, 2, 3, 4, 5, 6. Right, again you see, right, carbon 4 moves up, becomes the top of the chair from the feet. Carbon 1 shifts down, becomes what was the head becomes the feet. So on carbon 3 we wanted to have the big group axial, or equatorial, equatorial and up. What's on carbon 4? Nothing we need to worry about. Well, carbon 5. Where's the OH? Is it OH up or down? Up, so it's going to be what position? Equatorial. And the fluorine's going to be down, and it's going to be axial. So kind of like behind the whole thing there. Carbon 6 doesn't have anything. 1 has iodine. Iodine is up or down? Up, so it's going to be axial, equatorial. So that's even better, right? That's like, even if you're worried, if you're worried that this was too big, now they're both, right? These two big things are both equatorial, so that's good. What's on carbon 2 is a methyl. Is that up or down? Down, so it's going to be axial or equatorial? Equatorial. Right, because the axial position on carbon 2 in this case is up. So we want it to be down. So this would be the most stable chair conformation of this. Now you could go through and do the ring flip and add things in here, and you'd recognize that this 4 carbon piece is up. Here would be axial, which would be really bad, right? Because again, things would bump into each other. You'd have things in the axial positions things can bump into each other easier. So if you have something like this, a couple ways to go with this. To figure out how many, first you need to look at this and say, okay, does this molecule have asymmetric or chiral centers? Yes or no? Yes, it does. So of course the definition of an asymmetric or chiral center is sp3 hybridized and bind to 4 different things. So I think there's 2 carbons here that fit that bill. So one thing is if you have 2 stereoisomers, or 2 asymmetric chiral centers, how many possible stereoisomers are there? And that is 2 to the n, where n is the number of asymmetric centers, chiral centers. So here we have 2, so 2 to the n would be 4. So there's 4 possible combinations here of different structures, right? Stereoisomers. So let's draw all of those. And then we'll talk about the relationship to each other. No, things are crowded. Actually, I'll do. Okay, so here's a template for all of these. So if you want to have all the different stereoisomers, you need to have all the different combinations, which basically means you have two centers, right? Each center can be either be R or S, and so there's 4 combinations that would work for. So if we kept one the same, so let's just keep this as Cl and an F, and Br and an I. If we keep the Cl, this center the same, we can switch this one around. Those other ones we can switch this one around, keep this the same. Let's see, and then they're both switched. All right. Cl, and then I need to have it be the iodine in front and the Br in back. All right, so every single one of these structures should be different. Yes, they are. So we could go through and actually do R and S with these. You want to go through and do R and S? So go ahead and take a second and do R and S for every single one of these. All right, let's try on this molecule. So the first thing we do, we're looking at this chiral center, asymmetric center. We need to rank those things. So red, white, and blue, and then green. So what is the highest priority on this carbon? Iodine, right? Because remember, it's all about atomic number. Not about electronegativity, it's about atomic number. So this would be red. What's number 2? What's white? Red, white. So the white would be the Br. And then what's going to be blue? This carbon, A or B? A, right? Because it's closer over here. So blue and green. So now see if you can map that onto your thing. Let's do the other side. What has highest priority over on the other carbon? Chlorine. So that would be red. Fluorine would be white. Again, this way would be blue, and this would be green. So let's see if you can map that onto your molecule to see what we get. All right, we've reached a consensus, kind of. That one is S, and this one is R. All right, so this is R. So that means the one that's just like it, this would also be R. And then the opposite, right, when we flip the iodine and the bromine around, that would make this one S. Right, because it switches when you change wedges and hatches, it'll change. If this was S, one that's just like it, this would also be S. And then this one would be R because it's opposite. And this one would also be R. All right, so you end up with 4 different stereoisomers. And what they are to each other is also interesting. So let's call, I'll put an A in the middle here, a B, C, and D. So what is the relationship between A and D? What are A and D to each other? They're enantiomers. How do you know they're enantiomers? So A and D, everything's opposite. This is SS. Its enantiomer would be RR. So A and D, they're enantiomers to each other. Everything's opposite. A and C. What are A and C to each other? Diastereomers. They're diastereomers. They have one shared asymmetric chiral center, and then at least one other one that's different. So these two are diastereomers to each other. What are C and B to each other? They're enantiomers, because they're, again, this is R, that's S, that's opposite. This is S, that's R. They're opposite in every single asymmetric chiral center. So C and B are enantiomers to each other. B and D, what are B and D to each other?
Diastereomers.
B and D are diastereomers. They share one stereocenter and they have at least one different. Good. So there's 4 different possibilities here. All right, taking a look at number 14 from exam 2 from this from 2016. So our molecular formula we're given is C9H17Cl. So first thing you want to do, of course, is calculate your DU. So go ahead and do that.
A ring is 1
So-
saturation, right?
Yep, the DU here is 1, and that means we either have 1 ring or 1 pi bond. 1 ring or 1 pi bond. That's what that means. Good. So now the next section we want to work on is the IR part. All right, so here's our IR stretches. So 3033, that should tell you what? sp2ch. 2890 should tell you sp3ch. 1625 should tell you cc, double bond and alkene. Then 713 is that special region, and that should tell you a cis disubstituted alkene. A cis alkene. That's what that should be telling you. A cis alkene. So that tells us a lot, right? So that means we presumably would have an alkene with two H's on the same side, right? So that would tell us. Good. Now the next part we want to look at. Now we're not done. This just tells us an idea about the functional groups. Now we need to look at the HNMR. So lots of stuff written here for the HNMR. I would probably refer you back to your actual exam. In case you can't see this really clearly, I'll do my best to walk us through it. So the first thing you're gonna need to do is really just figure out who's coupled to who. That'd be the first thing I would do. So figuring out who's coupled to who, we want to look at the coupling constants. If the coupling constants are the same, that means those two things are 3 bonds away from each other. So A has 2 coupling constants. So if we look at A is coupled to who? There's 2 things.
B and C.
It looks like it's B and C, right? 10.3, 10.3, 5.4. Ooh, wait, no. B and D. Sorry, D. Okay. So we've covered B. B only has 1 coupling constant. B is coupled to A. A is coupled to D. What is C coupled to? 7.1. Who's C coupled to? C is coupled to F. And who else? 5.7. It's coupled to E. Coupled to E. Let's see. D is coupled to A. We have anybody left? We covered. Is that it? We're missing 5 points. C is coupled to 2 things. Good. So this tells you who's coupled to who. That means A is hearing 2 things, and C is hearing 2 things. That means, and also going back the other way. So that's who's coupled. All right, this is coupled. All right, so that's good to know. We start off thinking about this cis alkene. So why don't we just draw that piece in and see if there's any H's that match that description. Where are alkenes located? What part? What frequency? They're between 5.5 and 6.5. So these two, A and B, are probably our 2 alkenes. So you can call one of them A and the other one B. Right, they're both each worth how many H's? 1 H each. So we can cross those 2 off. Now we go back to here, look at, well, wait a second. Well, first let's do this. Let's subtract out. If we have C7, H, or C9, H17, Cl, we just lost what? We lost C2, H2. So now we have C7, H15, Cl. That's why you don't lose those. So we subtracted out our parts. So now where's HB? So we just talked about HB was coupled to A, so that makes sense. They can hear each other. Was B coupled to anybody else? No. But was A coupled to anybody else?
Yes.
Who was A close to? D. And D is how many hydrogens? 3. So that's probably what? A CH3. Right? So this is probably a C. And these are all HDs. Right? Because all they can hear is A. So let's subtract out that piece. Minus CH3. So C6, H12, Cl is left. Good. So we can cross out HD now. And actually we can cross out this whole piece right here. These things are covered now, aren't they? that coupling center is all done. So let's go to C. HC is worth how many hydrogens? It's worth 1 H, right? So let's say, okay, here's HC. Who's HC talking to? Both E and F. How many protons does E have? E is 3, so that's probably a CH3, right? And these are all H, what you said, E? Yeah. Good? And then HC is also coupled to F. How many protons is F? F was 2, right? F is 2, right? That's why it's important to copy things correctly. Yikes. So HF. That works. Notice, right, I don't know what's down here. But I do remember carbon has how many bonds does carbon always have? 4. So I don't know what's else on here, but I do know F and C need to be 1, 2, 3 bonds apart. And C and E need to be 1, 2, 3 bonds apart. This much I know from this. We can cross out this. We can cross out this. All right? So what do we have left? Now we got to subtract out something. So we had a 3 minus C3. How many H's is that? H6. So you end up with C3, H6, and a Cl left. We only have one more peak left, and that's 1.09 is single over 6 H's. So can you have a carbon with 6 hydrogens on it? No. Probably 2 CH3s that have no nearest neighbors, right? So let's draw in CH3. Don't know what's near. CH3. And these are all G's, right? So that, what do we have left then? So we can subtract out minus C2H6. So we have over the C and a Cl. So we probably have a carbon that's not bonded to any hydrogens then. And a chlorine, right? How are we going to figure this out now? So we have like 2 pieces left. We have a carbon and a chlorine. Carbon wants how many bonds? 4. And then chlorine wants how many bonds? 1. So here are all our pieces. There's 1. There's 1. There's the 2, a carbon and a chlorine. So now this is the hard part. Now you got to put it together. Now you want to go back and look at these frequencies and see if you make sense of those. So we did G. So now I want to go back and make sense of the frequencies. So carbon C, right? So these two make sense being on the alkene. Carbon C is pretty de-shielded. What do you think we should put next to carbon C? What do we have left that we can make it de-shielded with? The chlorine, right? Let's put the chlorine right here. So I would cross that piece out. Now what else? I mean, there's only actually one more way to do this, right? We need to connect between here, here, these 2 things, and then this carbon has 4 spots. So the carbon in the 4 spots needs to be in the middle, bonded to 1, 2, 3, 4 things. There it goes. And then you get it all together. All right. Obviously very complicated, but seeing the couplings is the key, and building it up from there. So we see there's 1, 2, 3, 4 spots open, and we have a carbon that has these 4 bonds. This carbon is bonded to all the last 4 pieces. This carbon is in between everything.
So the carbon connects to the big middle?
The carbon connects everything. This piece is bonded to that carbon. This piece is bonded to that carbon. This CH3 is bonded there, and this CH3 is bonded there. So this carbon's like the middle part for everything.